Welcome to your velocity, displacement, acceleration versus time graphs video. In this video, you will learn to find the displacement of an object from a velocity time graph, find the acceleration of an object from a velocity time graph, and find the instantaneous velocity of an object from a position versus time graph. This will help you do the displacement, velocity, acceleration worksheet you find on Schoology. So let's start by finding the displacement of an object that is moving at constant velocity. Hopefully you saw in the Moving Man simulation that an object moving at constant velocity renders a velocity time graph that looks like this, where there is no slope because the velocity never changes. So looking at this graph, we're going to figure out how far this object moved. So remember that for an object that's moving at a constant velocity, the velocity is the displacement, or change in displacement, divided by the change in time. I can rearrange that equation by multiplying both sides by delta t. And I can get the new equation of displacement is going to be the velocity. That looks like an x. Let's make it a v. Velocity times the change in time. So if I now relate that to the graph, I notice that the shape of the graph is really a rectangle. And the width of the rectangle is my velocity, and the length of the rectangle is my change in time. So if I found the area of that rectangle, it's going to match that equation. So the change in x is going to be velocity times the change in time. Velocity is going to be 10. The time is 5 to give me 50 meters with correct significant figures. Again, my units end up canceling out because the seconds in the velocity and the denominator cancel out the seconds on the time. So the moral of the story is this: to find the displacement of an object from a velocity time graph, find the area under the function. Let's look at an example that's slightly different. So what if the object is accelerating? Velocity is not constant. So what we are going to do is the same premise as before, where we know that delta x is going to be v delta t. But now my shape underneath my function is not going to be a rectangle. It's going to be a triangle. So if I take a look at this, I can use my equation for the area of a triangle, which is going to be 1/2 times the base times the height, which is going to equal the area, which is going to equal the change in displacement. This is going to be 1/2. The base is going to be my 5 seconds. My height is going to be my velocity of 20 meters per second. Same thing happens, seconds cancel out. I have 1/2 times 5 times 20, which gives me, again, 50 meters. So the only difference between this particular graph and the one before, same distance was actually traveled, but the object was moving at a constant velocity during this period of time, whereas during this period of time, the object was accelerating from a velocity of 0 to a velocity of 20 meters per second. Again, moral of the story: to find the displacement from a velocity time graph, find the area underneath the function. Now we're going to take a look at how to find the acceleration from this velocity time graph. So just like we did in the motion lab, to find the slope of the line, its rise over run, in a velocity time graph, the rise is going to be the velocity, and the run is going to be the time. So to find the acceleration, you're going to do rise over run, or velocity divided by time. And I can do this for any particular point in time on this velocity time graph because the slope is constant. So I'll have acceleration is the change in velocity over change in time. I'll have acceleration is going to be some value final velocity, some value initial velocity v naught over tf minus t naught. I can choose any 2 points for this. I'm going to choose, because it's easy, my origin as one of those points, and I'm going to choose, because it's easy, what happens to the velocity at 1 second. So my final velocity at 1 second is 4 meters per second. My initial velocity is 0, divided by my time of 1 minus 0, which is 54 divided by 1, or 4 meters per second. Again, all I did was find the slope of that line to get my acceleration, and I almost made an error there. My acceleration is going to be meters per second squared. Show you one more time how to get these units. Acceleration is going to be meters per second divided by seconds, which turns into meters per second times 1 over seconds, which is meters per second squared. That's how that unit comes into existence. This is how you find the acceleration from a velocity time graph. Now, we're going to flip over away from velocity time graphs and look at position time graphs. And when you've got a position time graph and an object is accelerating, the graph again is no longer linear, it's quadratic. And we are going to talk more next week why it's quadratic or has a function of t to the second power. So looking at this graph, I cannot use the method that I had already used to find the velocity from this position time graph, because if I was trying to find the slope from the first point to the last point, that clearly does not match the points that are on my curve. So this would be the slope, which would be the x over t, but that is not describing to me what is actually happening to the object. So I can't do that using a position time graph. Instead, I have to use something called instantaneous velocity. Please write down this definition in your notebooks. Instantaneous velocity is defined as the velocity at one moment in time. Imagine a cop with a radar gun on the highway. They take a data point of your velocity at that exact moment they pull the trigger. That's an instantaneous velocity. That's not an average velocity that you are traveling during your whole trip. So, in order to find that, what we go ahead and do is we make something called a tangent line. So, if I take a line and I draw it what we call tangent to the curve. What I mean tangent to the curve is I mean that this line will only touch the curve at one point, one and only one point. Hopefully you've experienced the term tangent before in your math class. We use that quite a bit in physics to explain what's happening with instantaneous velocity or instantaneous acceleration. Now, to find the instantaneous velocity at that particular point, what I'm going to do is I'm going to find the slope of that tangent line. So what I mean by that is I'm going to extend that out, really make my line nice so it looks like it's touching at one spot. And I'm going to find 2 points on that line. One of the points I'm going to put on the x-axis, and I'm going to put on the x-axis because it's simple. And we'll call that point, let's say 1.7 seconds and 0 for my position. And then this point, I'm going to call it 3 seconds and 20 meters. So to find the instantaneous velocity at 3 seconds, I use the fact that I'm going to have the velocity instantaneous be the change in position, the change in time, and I'm going to use the fact that we've got 20 minus 0 divided by 3 minus 1.7, 20 over, and mental math at this time in the morning is not working for me. 3 minus 1.7, 1.3. So 20 divided by 1.3 is 15 with sig figs meters per second. So at 3 seconds on this graph, at 3 seconds, my instantaneous velocity is 15 meters per second at 3 seconds. If I go to 4 seconds, will my velocity still be 15 meters per second? Absolutely not, because my slope of my tangent line changes. So what I would have here is a new tangent line. That tangent line is steeper, so it would have a new instantaneous velocity because the object is accelerating. This might take a little bit of practice getting used to. When you get to this problem on the worksheet, get a ruler and really practice drawing those tangent lines against your curve on your position time graph. So hopefully this will help you with the worksheet. There is graph paper up front if you need graph paper instead of writing it completely in your notebook. Have a good day.